Good day, ladies and gentlemen. This is the 14th lecture in the second series of lectures related to the implementation of the RM software for filter design. In this part, we will talk about designing of a corrector, a phase corrector, or designing of a group delay corrected selective low-pass filter. That means we will first design a selective low-pass filter and then introduce a corrector. The content is, as usual, naming the project, design requirements, synthesizing the transfer function, analysis of the properties, and then we will go to the physical realization in the form of LC, active RC, and SC, and finally digital infinite impulse response filters. We will start as usual by activating the main program and by allowing blocked content, and we will go to the recommended sequence. So what shall we do is we will name the project, and then since we are designing a low-pass filter, we will go the upper sequence. We will enter the design requirements. We will choose a selective filter, which in this case will be a critical monotonic amplitude characteristic filter produced by Papoulis, or the so-called Legendre filter. And then we will add transmission zeros to increase the selectivity, and then we will go to the corrector, which will allow to go to the synthesis. Okay, we will name the project as Legendre corrected. Now it is a low-pass filter design. We will enter the cutoff frequency, the upper frequency of the transition band, the maximum passband attenuation, the minimum stopband attenuation, the asymptotic slope will be fully free, the maximum group delay error, this is important here, we will put 2.5%. And finally, we will enter the normalization resistance of 1 kilo ohm. Now we will proceed with synthesis of critical monotone filter of type 2, and the program suggests that we should use 9th order filter, but since we will be introducing zeros, we will go with 7th order filter. And that's done. Now we are producing the polynomial low-pass critical amplitude characteristic monotonic filter of Legendre type. That's done. We proceed now with amplitude correction, which means we are introducing transmission zeros, and in this case we will introduce only one pair of transmission zeros, and this program will create a new transfer function having one pair of transmission zeros based on the Legendre solution. Now we go again to amplitude and phase correction, and we will go for group delay corrected selective low pass filters. And the corrector should be defined. We will enter fourth order corrector and start the corrector. Since it is an iterative procedure, which already started, we will pause the recording. So the iterative procedure finished. We will proceed with the analysis of the properties of the solution. In fact, we were supposed to analyze the filter before introducing the corrector to conclude whether the amplitude characteristic satisfies the imposed requirements and to adjust the order of the filter and the number of the transmission zeros. But in order for the video to be shorter, we skipped this step, behaving as if everything is acceptable. Now we will go to the results of the low pass analysis. And first we will look to the time domain response. Here is the step and the direct response. You can notice now that there is a ringing before the pulse, which is due to the complex transmission zeros introduced by the corrector. But also you can notice the symmetry of the pulse response, which is very important for pulse transmission and for rejecting intersymbol interference. Now we will go for the frequency domain response. And here it is. So this is the amplitude characteristic. We will come back to it. Let's first see the complete story. This is the phase characteristic. As you can see, is extremely linear. This is the passband amplitude characteristic, and this is the group delay. I will enlarge a little bit the scale to see. This is 20 microseconds, and this is 30 microseconds. And here is the enlarged scale. We will put here 150. Here it is. So we have a fourth order corrector which controls this, and this point. And this is a benefit of the algorithm. So practically this extends the approximation interval thanks to the nature of the curve, which has this sharp spike at the end of the passband. Now let's go back to the amplitude characteristic, to the attenuation. And let's see what is the frequency where 40 dB is first reached, not 35 to 45, and here from 100 kilohertz to 150 kilohertz, to see how it looks like. And this, as we can see, is much more selective than 150, what we were asking for, so that we probably could go even with fifth order filter. Now we may proceed with the synthesis. First we will go with passive LC, low pass. Done. Let's see the SPICE file. Here it is. The group delay. As you can see practically this, but the logarithmic scale is compressing the upper frequencies, so the ringing is here at the upper part of the passband, but everything okay. So this was the SPICE analysis results of the passive LC circuit. Now let's see the passive LC circuit, how it looks like. This is the schematic cascade. So there is capacitor in parallel, inductor in series, capacitor in parallel, inductor in series, and then this is the P cell, which is realizing the transmission 0 at the omega axis, and these are the two complex cells realizing the complex transmission zeros of the corrector. And it is, of course, finished by a capacitor to compensate for this negative C2 somewhere here. Okay. Now we may go to the RC realization cascade. And let's see the SPICE file. So of course it is okay. Now we go to the schematic of the active RC, so second order cell, then realizing the transmission 0. This is a complex transmission 0, this is another complex transmission 0, and the rest are low pass second order cells, finished with a first order cell which is inverting. Now we will go with RC parallel. RC parallel produces a spice file which will be open now, and we will see the results, which are of course the same. And now here is the schematic of the RC parallel, which is always the same, only the number of cells is different, 1, 2, 3 second order cells, and so everything is here, 1, 2, 3, 4, 5, 6 second order cells, and 1. Yeah, of course, we have the corrector. Okay. And now we go with the SC. It asks for the sampling frequency and the capacitance. And now we will run the synthesis program. Done. The spice file is here. We will look for the, after the second stage of the anti-aliasing, this is the response. We will not wait for it to be finished since it lasts long. And here is the schematic. Of the SC, so these are, it is in fact 11th order filter because 7 plus 4, 1, 2, 3, 4, 5, and 10th order until here, and 11th order here. And this is the summing and the anti-aliasing, sample and hold, and the whole system. Now, finally, we will go to the digital infinite impulse response filter. This is the sampling frequency, and here runs the synthesis program. This is the report file. Here are the coefficients, and this is the CSV file, and we will look to the response in the frequency domain. Here it is, and we will go one after the other. So this is the attenuation, this is the phase, this is the gain, and this is the group delay distorted by the bilinear transform. Okay, that would be all about the synthesis of group delay corrected selective low-pass filters. In this case, it was a Legendre extended with a pair of transmission zeros. Thank you for your attention.